All right, so my idea here is to try to go through these IB problems and look at each one for the right answers. The focus is a little funky because it's not actually a document camera, but we'll do our best here. And if you have your own copy, that would help a lot. So it's no calculator, so no calculator because it's multiple choice. And let's go ahead and do these. So 13 is looking at a pendulum. It's moving back and forth. And we can see that clearly when it's moving its fastest is at Y. And then as it moves back and forth, since it's a simple harmonic oscillator, it'll have maximum acceleration at either of the two ends. So the right answer here is B, because we have maximum acceleration at X and at Z. And then we have 0 at X and Z for the linear speed. Again, maximum acceleration at the edges, and then 0 at the edges for the linear speed, since the maximum would be at Y for linear speed, as it rotates back and forth with simple harmonic motion. All right, let's keep moving. For 14, looks like we have to decide if each one of these are true. So some of the properties that can be demonstrated using waves. And clearly we can see that with sound waves, we would not have polarization, but we'd have all other things. So 1 and 3. So B is the answer there. We know that sound waves cannot be polarized because they're longitudinal. And that's the reason for that one. Looking down to 15, we can see that the amplitude of a wave is given, and its intensity, the amplitude increases by 4a, so the intensity, since intensity is the square, because we know that intensity is proportional to the amplitude squared, we can say with clarity that since the amplitude is 4 times bigger, that we get 16 times bigger for I. So D would be the answer to 15. For 16, looks like we could say that the speed is going to speed up when you go across a medium. We usually talk about angle in addition to that, but we could talk about that if it's going fast and then it slows down, or if it's going slow and then it speeds up. So this would be the fast area. And the fast area has a small n, where the slow area has a big N. So if that helps you think about it. You also have the equation booklet, so you could be using the equation booklet and doing the ratio way of doing that. But in any case, if you're careful and make sure you label each side properly, it's pretty clear that A would be the right answer on 16. But make sure if you've labeled an area 2 that this area stays 2 for N, lambda, and V, and then similarly for the ones. Well, let's take a look at 17 then. Looks for 17, you have an open pipe and a closed pipe. So the fundamental here is going to be different than the fundamental here. And so it's clear that the fundamental here has 1/4 of L would be the wavelength. So L over, lambda times, lambda divided by 4 gives you L here, where lambda divided by 2 gives you L here. And let's see what the question's asking. Closed on one, open on the other. What is correct about, about the harmonics? We learned that pipe X has all of the harmonics. Pipe Y has only the odd harmonics, which is why we clearly would get B then for the answer to 17. On 12, let's see what we're graphing. Here we have displacement X, it looks like. Displacement X is on the X-axis, and we got to be careful here. Acceleration A is on the Y-axis. So we know that if you have simple harmonic motion, that it's proportional, which makes you want to go to B, but remember it's going in the opposite direction also, which is why the answer is A and not B. These are wrong. Awesome. Hopefully you have your own copy as you're going along with this. We're now on 15. What is the best estimate for the refractive index in which light speed is at 2.7, which is about 2.7 times 10 to the 8th compared to 3 times 10 to the 8th. And so our ratio there, when we divide these this way, by the way, you know that the index has to be greater than 1, so A is obviously incorrect. So it looks to me like you got to go with C for 15, okay? And you don't have a calculator, so we don't have time to do that. If we were to be checking it, we see that is correct. But remember, you don't have a calculator, so it's okay that the answer is a little bit off there. It's clearly not 2.7, so that's what we would do. 11, for simple harmonic motion, we know that the restoring force acting on the system is proportional, but in the opposite direction of the displacement. And they're saying from equilibrium, which is why they're not saying in the opposite direction. But that's pretty clear why 11 would be the right answer here. When we go to 12, it looks like at 0.0 only would be the right answer because it's in equilibrium only as it's oscillating between the extremes, only as it goes through the middle. So these two springs are fighting each other and they would be equal in force pulling on each other at the equilibrium point only. Remember that if you're to the right of the equilibrium point, the restoring force will be to the left. If you're to the left of the equilibrium point, the restoring force will be to the right. And that's because this is simple harmonic motion, and that gets us the answer of B for number 12. Okay, let's see what we get after 14. Ooh, tricky question. It looks like we're coming this direction, and then we're speeding up and going like this. So we see the wave fronts coming like this, and as it speeds up, it moves away. If we were talking about the angle, this would be the angle here. Theta is bigger than it is here. This theta coming in is smaller. So we know it's speeding up when it goes to the other side, and so it should be faster on that side. Okay, and then we want to think about how the ratio works, and remember that when it's slow, N is big. So we think about the ratio in those terms, and then we can look at the relative distance here. You actually don't have a ruler during the test. You could estimate that distance compared to that distance as a ratio, and it looks to me like it is bigger by a bit, and then we got to think about which way they're doing the ratio. So the refractive index of 2 to that of 1. So we're saying N2 over N1. And so we got to have it here, N is small. How do we know N is small? Because it's moving fast. It's moving fast, N is small. So N2 is the small one. So we have the small one on top. So that means it has to be less than 1. And it's obviously not 2 times different. So we can get rid of A. So without a calculator, without a ruler, we got to figure out that this thing is indeed 0.67 because these won't be possible, this one won't be possible. Kind of a tricky question there, I think. So now we go to this one, and I've run out of time. I don't like my videos to be more than 10 minutes, so maybe I got to speed up a little bit here. In any case, it looks to me like P is going to be going down because this crest is moving this direction. P will only go up or down. So these ones here are garbage. C and D are obviously garbage. Is it going to be going up or down is an interesting question because once this pulse keeps moving to the right, it's going to be back to being flat. We know that actually it's on its way down at this point. And so B will be the answer. When we look at this one, we got a little tricky situation. This is a complicated question. Looks like the variation of T of displacement undergoes simple harmonic motion. Which graph shows the acceleration of the particle?